Right, so in the last video we separated the time-dependent Schrödinger wave equation in order to find the time-dependent Schrödinger wave equation. This is just a look at what we had at the end of that. So now what we're interested in doing is looking at what's called a steady state, or sorry, a stationary state of the Schrödinger wave equation. So what you're now going to look at this little part of the equation. We've already looked here at the left-hand side of it and called it the time-independent Schrödinger wave equation. Now we're going to look at this part of it, the part of the equation that is independent of space but dependent on time. And I've just rewritten it out here, a little bit neater, a little bit clearer. So what we're going to do is we're going to try and solve this partial differential equation. And actually, these, just as a note, I noticed, can actually be written as full derivatives. Why can they be written as full derivatives? And I should correct them back here. The reason they can be written as full derivatives is because chi, which is being derived, is a function only of time. So its partial derivative with respect to time is exactly the same as its full derivative with respect to time. It is only partial derivatives are only what we use when it's a function of multiple things and we're only looking at one of them. Since time is the only thing chi changes with, it will change with t. It's a full derivative. What we're going to do now is we now have a nice, easy first-order differential equation, an ordinary differential equation. So, what we're going to do is I'm just going to offer a little note. I'm going to first tell you that this equation can be written as IH bar d ln of chi. That's my tablet acting up. My tablet is still acting up. D ln of chi dt, which is going to be equal to h bar omega. Make that an actual h bar. Right. Why can I do that? That doesn't really seem very intuitive, does it? d chi dt multiplied by 1 over chi is equal to that. Why can this lump be rewritten here as this? Well, I'm just going to draw it off to one side by just to note that the integral of 1 over chi d chi is going to be equal to, now that is nice and simple, we know what that is. That is ln of chi. If my laptop would actually let me write chi. That is ln of chi. Okay? So what we can say from that is actually, if we get rid of this, we can actually then, from that, we can say that if we if we sort of undo both sides, we differentiate them instead, what we'll get is 1, if we differentiate both sides, we'll get 1 over chi d chi is going to be equal to the change, or the infinitesimal change, in the log of chi, the natural log of chi. So here we have this bit, and all we have to do now is just divide both sides by an infinitesimal change in time. Since we're doing it to both sides, it's not changing the equation. And now we have, if I can write the t in a sensible manner, now we have this thing is just what we've done here. We've said this thing here, and we replaced it with this thing, which is here. We draw a box around that to make it clear that it's one thing, if my pen will stop jumping. So that's where that's coming from, why we can say that. So now, what do we do? Well, now what we do is we're going to move this lot under here. We're going to move this over here. What we're actually going to be doing, of course, mathematically, is we're going to be dividing both sides by IH bar. So this will cancel with its IH bar, and this will be divided by IH bar. And what that brings us to is going to be d dt of ln d dt of ln chi, which is going to be equal to minus minus I omega, because 1 over I is minus I, so that can be brought up to being minus I, and h bar over h bar is 1, so we don't write the 1, so we get minus h bar, or sorry, minus I omega as this thing. Now what we're going to do is, now we have an even simpler differential equation that we can separate the variables, multiply both sides by dt, so we get minus I omega dt, multiplying both sides by dt. And what we can now do is integrate them. That doesn't look like an integral. That's what an integral looks like. Right, so we've integrated them, or taking the antiderivative of both sides, or the indefinite integral. Just to note why we can do this, because these are a constant. Minus I is a constant, complex constant, but it is a constant, and this omega is also going to be a constant. It's just a number. It's not a function of anything, at least not for our purposes. This is starting to get on my nerves. At least not for our purposes. So what we get there is, we now say that we have ln of chi is going to be equal to minus I omega t plus ln of a, where a is just some constant. What have we done here? Why has we got this ln a term on the end? Well, that's simply because it was we've taken the constants of integration from both sides and brought them together to make one constant, because we can do that because they're just constants which can be added and subtracted. And it's going to be, in a moment, it's going to be nice and easy for us if this constant is the natural log of another constant, which we can also do because the natural log of a constant is itself a constant. So we say, so this is how we're writing our constant of integration. Because from there we can now say, if we raise both sides by, if we subtract this from this over here, we get ln of chi over a, that's just the properties of logs if we're subtracting ln a from both sides. If you're not happy with that, go back and revise it. It's in any mathematical handbook, and any decent textbook will show you in more detail why, if you play around with the logs. So that's law of logs. And this side is going to be I omega t. From that, what we can get is, if we raise now both sides to the power of e, or as e to the power rather, well, e to the power of a log is just the argument of the log. Sorry, a natural log, I should say. E to the power of a natural log is just the natural log. It's the argument of the natural log, which is chi over a. And this side will be e to the power of minus I omega t. Draw that out. Okay? Which we can rewrite by multiplying both sides by a, as chi is a function, or sorry, is a, sorry, I'll write that more neatly. Chi is just a e to the minus I if my computer will let me write ae to the minus I omega t. Okay, so this is our solution for chi. Remember, this is the solution only if the potential energy, as we found back here, this is the solution if the potential energy is only a function of position, not of time. This is what we get for the time component of our wave equation. So the full wave equation, capital psi, is now, I don't even care anymore, is now going to be, okay, I do care about that, is now going to be phi e to the minus I omega t. Just in case you're wondering where the a is gone, we've just put it in here in phi somewhere. It doesn't particularly matter, because it's constant, we can just stick it in wherever, and it's nice and neat if we write it this way. Forget about the constant, stick it in there, phi. Now what we see here is that this thing is simply modulating the phase of the wave function. It's not actually changing it. The wave function is a function only of the position, but its phase is a function of time, but the actual end result of the wave function is of position. This is why we call it a stationary state, because the wave is not changing. The next video will look a little bit more, be a bit more thorough, and look at the probabilities and show that the probability of finding a particle at any point in space is constant, given that the potential is a function only of position. We'll show that the probability of finding a particle at any point, which is the actual physical thing, as opposed to the wave function, which is just a mathematical way of storing information, we'll find that it is constant in time. And that's why we call it a stationary state.